We cope with uncertainty by assigning subjective probabilities to the alternative outcomes associated with an event or lottery. Suppose a potential investment has three possible outcomes, yielding $160,000, $200,000, or $240,000, with outcome B being the most likely. By assigning probabilities to each outcome, we estimate the expected value of the investment, weighting the value of each outcome by the probability of observing it. If outcome B has an 80% chance and outcomes A and C 10% each, then I can multiply P times V and sum to get the expected value, here 200,000. Imagine that I have a second investment opportunity with the same possible outcomes, but quite different probabilities. The second investment has the same expected value, but with much greater uncertainty over which outcome will arise. The second is much riskier. We characterize risk by measuring the dispersion of the outcomes around the expected value. The two primary measures of dispersion, you will recall, are the variance, which is computed by squaring the deviation of the value of each outcome from the expected value, weighting each deviation by the probability, and summing across all the possible outcomes. Or we use the standard deviation, which is the square root of the variance. It has the attractive feature of being measured in the same units as the expected value, that is, the values of each potential outcome. To obtain the variance for the first investment, subtract 200 from the value of each outcome. For example, 160 minus 200 equals negative 40. Square it and multiply by the probability, then sum up to get a variance of 320. The square root of 320 is 17.9. Now stop the video and take a few minutes to fill in the cells of the second table and calculate the variance and standard deviation for this second investment. The second investment has a much higher standard deviation. That is, it is much riskier even though it has the same expected value. A risk-averse individual, one who has a diminishing marginal utility of income, would prefer the first to the second, which we can demonstrate by assuming a particular utility function having this characteristic. The second derivative of this function is negative. So the marginal utility falls with V. Assume for simplicity that the investment we have been discussing determines the complete wealth or income of the individual. Utility comes from consumption, but for a fixed set of prices, utility maximization will yield an indirect utility function that describes the satisfaction generated by the consumption that will result from the income or wealth we command at each possible outcome of our uncertain investment. The expected utility from the investment, or any uncertain event, is the sum of the utilities from those outcomes weighted by the probabilities. For the utility function I have assumed, the utility from outcome A is the square root of 1600, or 40. 10% of 40 is 4, and the weighted utility for outcome C is 4.899. Summing the utilities weighted by the probabilities yields the expected utility 4.899. 0.068, rounded to the nearest thousandth. Now stop the video and you do the same for the second investment. Take care not to round too soon during the intermediate calculations. Here's the result. The expected utility of the riskier second investment is lower than that for the first. And the individual will prefer $200,000, the expected value, with certainty to risky investments with the same expected value. Hence, a risky investment is going to have a higher expected value, or alternatively, a risk-averse individual would be willing to pay a risk premium to avoid the risk associated with any uncertain event. We can't observe utility functions, but we can infer preferences from the way individuals rank the expected values of investments or other uncertain events.